Here is a rotating wheel. Here's a point on the rotating wheel. And everything I said before applies here. Okay. So I guess by now you guys hopefully are getting a sense. As soon as you see this, you're thinking, what's the very first thing that comes to your mind? Calculus. Calculus is the first thing that comes to my mind. And then maybe the second thing I'm thinking, is this going to be variable or constant acceleration? And I'm betting, I guess I would bet right now, I'm going to bet that this is variable acceleration. Although that, you're going to lose that bet a lot, and it doesn't matter if you lose, but this is my position function. And it's not position in the sense, I'm not talking X or Y or Z or just general vector R position. I'm talking about theta, angular position. So the mapping is pretty close, but there are some notable differences, and we can focus on the nuance differences, which I think makes this chapter go pretty well typically. But I am thinking calculus. I am thinking, well, this is probably not constant acceleration, a constant acceleration situation, but those are my thought process. And then our first question is, at t equals 0, where is this point? So let's do part A. Part A is plug and play. At t equals 0, we would say, well, theta, and the argument to theta is t. At theta at t equals 0, 0 equals just plug and play, 5.84 plus 1.31 t squared plus 1.13 t cubed. And let's just plug and play and get the right answer at t equals 0. Well, I guess we're done. At t equals 0, the answer is 5.84 radians. 5.84 radians. That is the answer to part A. If I just evaluate that given function at t equals 0, don't need to do anything than just look at it. The one thing this is the major nuance of this chapter. It's the whole notion of radian. So radian is the big new topic in chapter 10, I think. Radian, the radian. And then I talk about, here's the definition of radian. A radian is defined as S over R, where, let me show you what S looks like. S stands for arc length. So I'll just repurpose this arc here, or this circle here. I'm going to trace out an arc length, like right there. So this is S. This is S, and S stands for arc length. And here's the radius. The radius, well, here's a radius. And then I guess here's another radius right here. So it looks like a pizza slice. So think of this pizza slice, and there's some important labeling we have to do. S stands for arc length. Arc length. And it could be a portion of a circle, or it could be one circle, or it could be multiple circles. If this wheel spins 5 times, then you have 5 circumferences that correspond to the arc length. This is R. R stands for radius. And this is theta. Theta stands for angle. So this is our new, I refer to this as birth of a radian. Birth, not birth of a nation, birth of a radian. Birth of a radian, or just BOAR. Birth of a radian for short. Birth of a radian is just, and I always go back, I always reset myself mentally to this point. This is what a radian is. Radian is just taking this arc length, whatever it is, divided by this radius, whatever it is, and that's what we're going to call a radian. There was a great animation, I think, that really kind of showed this visually very well in the lecture video. right, so that's what a radian is. And you might ask yourself, why are we dealing with radians? Can't we just be happy with degrees? I mean, everyone knows about degrees, but it turns out typically radian is a much more convenient way to deal with stuff that spins and angles and rotation. And here's a little trivia question. What are the units for degrees? The degree. What are the units for the radian? There ain't no radians. There ain't no units. Because technically the radian is a ratio. So if I do dimensional analysis, what's the dimensions of S meters? If I do the dimensions of the radius meters, so in this case, I would have meters over meters, so it's unitless. And a lot of the stuff in physics and engineering is based on radian, based on this relationship right here. So I'm spending a lot of time on it, even though I spent a lot of time covering this in the lecture video, because again, I think this is a fundamental introduction, an important introduction. Let's do part B. At time equals 0, what's the velocity? So this problem is, I think, almost identical, if not identical, to a problem we had, I think, on the first day of class, or in regular old linear kinematics. At t equals 0. Well, I'll write this before I do that. Well, velocity is defined as d theta. Oh, wrong velocity. Velocity is defined as d theta dt. And let's be good on names. It's important to use the right terminology. You don't want to be embarrassed. This is called angular velocity. Angular velocity is how we popular kids refer to this. And this actually is Greek letter omega. So what that variable is called omega, and it stands for angular velocity. This is theta, as we all know, Greek letter theta, and this stands for angular position. So there really is a correspondence here. Just like in the good old days, we had position, and we had change in position, and we had velocity and change in velocity, and time, or I should say, and acceleration and time. We have the same thing in the linear world. We have theta and change in theta, and omega and delta omega, and alpha, which we'll get to soon enough. But let's just figure out, what is the velocity of this flywheel? It's a flywheel on your engine. What is the velocity of this wheel at time equals 0 seconds? Let's take the first derivative. So that means I have to take the first derivative with respect to time, the derivative with respect to time of my function 5.84 plus 1.31 t squared plus 1.13 t cubed. And if I do that, the power rule says I'm going to have 2 times 1.31 t plus 2 times 1.13, or I should say 3, sorry, 3 times 1.13 t squared, and we're going to evaluate that whole thing at time equals 0, and the answer is 0 meters per second. Sorry, that's embarrassing. 0 radians per second. All right, great loss of face. But this is the answer to part B. And I guess we're just worrying about position and velocity at this point. Oh, no, we're going to get to angular acceleration. What is the angular velocity at 5.01 seconds? So let me just highlight this. So just evaluate your velocity function at some time value other than 0. And that's going to be quick and easy work. Number 3, part C is I'm just going to take my velocity function. So I'm going to write it like this. Omega, angular velocity at time equals 5.01 seconds equals 2 times 1.31 times t, 5.01 seconds, plus 3 times 1.13 times t squared, 5.01 seconds squared, and then calculator time. Okay, 98 and some change. It's interesting. Technically, my calculator value varies a little bit compared to Wiley. I'm definitely within that 2%, and the answer here would be radians per second. Okay, so that's part C, 5.01 seconds. Let me just do 2 times 1.31 times 5.01. Okay. Oh, no, I guess I got this right answer. Fine. All right, so good. So we're counting down the oldies. A is done, B is done, C is done. Calculate the angular acceleration. So this is great. I can kind of go at a pretty high velocity clip for all this, no pun intended, just because we've covered a lot of this basic kinematic stuff before. So this is it. Like I said, this is where a lot of times the light bulb switches from dimly lit to brightly lit. All right, so D says, what is the angular acceleration? This is Greek letter alpha. Greek letter alpha is defined as d omega dt. Just like in the good old days, we had velocity was defined as dx dt or y or z. Now we have omega is defined as d theta dt. And in the good old days, we had acceleration is defined as dv dt. And now we have angular acceleration, Greek letter alpha, is defined as d omega dt. So now we just take the derivative with respect to time of my omega function, and I'll just do the power function right now because I do have my velocity function sitting right here. So I just need to differentiate this with respect to time. So I'll just do that right now. That would be 2 times 1.31 plus 2 times 3 times 1.13 times t. All of this evaluated at t equals 5.01 seconds. No, 1.67 seconds. Erase. 1.67 seconds. Okay. Radians per second squared. Kind of like giving the cold shoulder to units. But maybe I'll just say, hey, I'm not spending any time on units, but don't forget to do dimensional analysis because that is a great way to keep out of physics jail. All right, so that was D. Radians per second squared. Not meters per second squared, radians per meter squared. And last but not least, I think they have an open-ended question here. Is angular acceleration constant? The answer is no. So there you go. You shouldn't think about, you should just look at my screen and say, well, if Chris's screen says no, but the answer is no, because right here, this is my velocity function right here. That's my velocity function. And the answer to the question, is this constant or variable? I should say acceleration. This is my acceleration function right here. Let me start over. And you can see this means, this means acceleration is variable. It varies as a function of time. So just just if you have a variable in your expression for, if your acceleration expression is anything other than a constant, then that means it's variable. This means acceleration is variable or varies. It's not constant. So the answer is no. All right. Look how much fun things are now. Really is just a good chapter 10 is great just for this purpose. Because so many new things are flying out at you at the beginning of the semester. It can be overwhelming, but hopefully now it's just whelming, not overwhelming. Let me get quiz 2 ready. Chapter 10, quiz 2. It's now 6:22. Okay. Hopefully you are seeing what I'm seeing here. Chapter 7, chapter 10, quiz 2. It's another flywheel, and I keep using this flywheel analogy because flywheels are really interesting. They're really kind of at the forefront of a lot of modern applications. And maybe what I'll do, flywheel, maybe flywheel battery, or even better, there's something called a kinetic energy recovery system. Not the greatest spelling, but it worked. Here. Okay, so many examples of flywheels, but this is one. Let me open it in a new tab. Kind of hard to see, but not the highest resolution. But these are kind of mainstays of a whole bunch of vehicles, and this is a Formula One vehicle. And you can see there's something here called a KERS, a kinetic energy recovery system. It converts kinetic energy into electrical energy and back again. So, this is talk about torque on demand. Anyway, where is this little flywheel thing? It's right here. There's this little device right here. You can see the leader line to it. And this is pointing to a little hunk of metal that spins really fast. And I guess if we get a closer view, here's a pretty good looking picture, I suppose. This is what it looks like more up close and personal. That's pretty large. Okay, let me reset. There. All right, so inside, this is an enclosure. Inside you have a spinning disc. It's actually all not that sophisticated. It's just it's a wheel. It's like a potter's wheel. It's a spinning wheel that spins around and around. And typically, this is where it does get pretty interesting. It's spinning inside that enclosure. It's a vacuum. So you draw a vacuum and you levitate it via magnets. So if it's spinning in a vacuum, that's cool because you don't have air resistance. And if it doesn't have a physical based bearings, if there are no physical bearings, it's just spinning within a magnetic bearing, meaning no contact, then that means no friction loss, no air resistance losses, no friction losses. So it spins pretty freely, and basically this is a simplification, but if you slam on the brakes, you spin this up, this becomes energized, and then when you want to accelerate, you tap into this really fast spinning hunk of metal, hunk of steel, and it's instant torque. You really experience a profound acceleration. So anyway, just thought I'd mention that just to take a break from doing problem solving, because this is pretty mentally taxing. But that's why I keep referencing flywheels, and there's more examples too. But this is very familiar. So now, at the risk of going too fast, I'm not going to go too fast. Tell me if I'm going too fast. But let's just say, let's just do the calculus thing. Let's go ahead and make sure everyone's feeling good about how to do derivatives at 1.01 seconds and 8.9. What's the angular velocities? So this is going to be a little bit different. This is not a copy and paste of the prior. There's going to be a little bit of a wrinkle here, but right now, A says, what's the angular velocity? So omega equals d by dt of theta, and theta is given as 9.32 t minus 5.43 t squared plus 3.22 t cubed. So here's my omega function. It's going to be 9.32 minus 2 times 5.43 t plus 3 times 3.22 t squared. And you know what I should do? Everything like that. And then I should include radians per second. And then I'm evaluating this at time equals 1.01, and then again at 8.98. Okay. And then we'll get into the slight variation here. 9.32. Radians per second. That's the answer to part A. Go ahead and do the answer to part B, and then we'll talk about part C. That's part A. There's part A, there's part B. Part C. What's the average angular acceleration? All right, so this is where there's an exciting difference. We'll call this step 2. Step 3 maybe all the way over here again. Part C says, what is the average angular acceleration? In the olden days, old school, we had acceleration was defined as change in velocity over change in time. Now in the rotational world, we don't have acceleration. We have angular acceleration. Alpha is equal to the change in angular velocity over the change in time. So I'm just going to do final minus initial. Final minus initial is at 8.98 seconds. I'm going to do, here's my final, let's do omega final minus omega initial over T final minus T initial. That's what delta means. This corresponds to omega initial because it happens at the earlier time. And this is omega final because it happens at the later time. So if I just go ahead and reuse those numbers, I'm just going to do calculator. Well, I put this in calculator memory location A. And I put this in calculator memory location B. So it's going to be secant B minus secant A all over 8.98 minus 1.01 seconds. So this will be my average angular acceleration. Okay. Again, careful with units, radians per second squared. That's the answer to part C. Step 4. Okay. What does part D say? Part D says, what's the instantaneous angular accelerations? And so now here's, and this is for comparison purposes, but right now let's just go ahead and follow orders for part D. Part D, what's the instantaneous angular accelerations at the beginning and end? So let's do for part D, alpha, instantaneous alpha. This is average. This is average alpha, average angular acceleration. This is instantaneous acceleration. So let's see if this is my angular velocity function right here, which results from taking the first derivative of my position function, then I'm going to take the first derivative of that to get my acceleration function. So I can just do that kind of right on the fly. I'm going to take the first derivative of this expression for angular velocity. And if I do that, I'm going to get negative 2 times 5.43 plus 2 times 3 times 3.22 times t. I guess that's it. And I need to evaluate that at the beginning of the interval, at the beginning. So the beginning is at t equals 1.01 seconds. So this is the blink of an eye. If I just blink my eye, just like snap my fingers and say, hey, I don't care about the average acceleration. I just want I want the acceleration at this moment in time. That's the difference between average and instantaneous. Minus 2 times 5.43 plus okay. $8.6532 radians per second squared. That's the answer to D for instantaneous acceleration, standing in stark contrast to average acceleration. Then we're going to do the same thing again, except just at the end of the interval. So the instantaneous acceleration at the end of that interval, just evaluate it at t equals the end of your interval. Okay, that's the answer to part E. And we're done. Pretty plug and play, but good to maybe clear some cobwebs that may have built up as far as kinematics is concerned. Calculus-based kinematics and algebra-based kinematics. And I think one of the, well, there's no real moral to say. The only real sort of, concluding comments to make is, hey, look at the difference. This is my average angular acceleration, but certainly that doesn't mean that it doesn't vary significantly. My angular acceleration varied non-linearly, or actually technically linearly, I should say. My angular acceleration did vary linearly, because this is a linear term, from that beginning value to this final value. So I guess that's the only sort of concluding comments I can scrape up. Other than that, this is just sort of just a practice, burn up type of exercise. So let me get to work on quiz 3. I'm coming back to this. Quiz 3 will be 1017.
Hey, excuse me? I
Yes.
was wondering something. How come the instantaneous velocity for the final time and the initial time, like the difference between them isn't the same as the average velocity, the average acceleration?
Because that's the difference between average acceleration and instantaneous acceleration. So that's actually a good question. Yeah, we're not just taking the average of two values, endpoints, because the acceleration is not constant. That is a good concluding comment to make. All right, so quiz 3. It is now 6:39. Okay, chapter 10, quiz 3 is now available. Chapter 10, quiz 3. Okay. Another big old multi-part problem, but usually problems like this, every step is kind of rudimentary, but the sheer number of these steps makes it kind of time consuming. But so, I mean, that's one extreme. Do you want time consuming yet pretty methodical, or do you want, well, that's your choice. Or do you want time consuming and, brand new thinking? I don't know how much new thinking is involved here. Let's see. This is chapter 10, quiz 3. A flywheel. So they're coming right out and saying we have a flywheel. Okay. There is some new. Well, I don't know if it's accurate to say new thinking, but we're getting into some new practices. Although we've seen it, so we're recycling some practices. So here's a flywheel right here. There's my flywheel. And then there's a reference line. So they're saying you have a flywheel at time equals 0. The reference line is at 0 radians. So let's draw that. Here is my reference line right here. From the center of that circle. That's it. Let me try that again. Uh-oh. While I restart. Reference line at time equals 0. They're saying we've selected a reference line, and the reference line we selected is at 0 degrees radian, or zero radian. That's technically incorrect. So never say that, especially in social situations. It's greatly embarrassing if you say 0 degrees radian is grounds for shunning right there. It's 0 radians or 0 degrees. Okay, so that is our reference line. This is theta equals 0 degrees. Theta naught, I guess they're labeling it. All right, anyway, the flywheel at time equals 0, the flywheel has an angular velocity. So this number here, I would say omega initial. This is omega initial, just like you remember the kinematics variables. You remember x initial, x final, vx initial, vx final, a sub x, and t. We have the same thing going on here, except now it's theta initial, theta final, omega initial, omega final, alpha, and t. So they match up very nicely. And notice that, time in the linear world is same as time in the angular world. All right. So we know they're basically giving us a bunch of kinematics variables. This is alpha, reference line through what maximum angle theta max will the reference line turn in the positive direction? We should talk about what's positive direction. I think the convention is CCW. CCW is taken as positive. CCW is positive, and that same convention says CW is negative. Counterclockwise is taken as positive. Clockwise is taken as negative. So they're saying that, all right, here's what's going on. It's good to see the forest through the trees here. All right, at time equals 0, this wheel is spinning in the positive direction. So ready, set, go. All right, this is my initial angular velocity. My initial angular velocity is given as 9.3 radians per second. And this is the positive direction. It's positive because positive means counterclockwise. That's the convention. You can flip that convention if you want, but unless there's a reason to, why not just stick with the convention? So now you guys know what's going to happen. Initially, this flywheel is spinning counterclockwise, but it has a negative angular acceleration, which means it's slowing down. So as soon as you look at this situation, it's slowing down because I have my angular acceleration going in the negative direction. Negative is considered to be clockwise. This is alpha. Alpha equals negative 0.35 radians per second squared. And that's just given to us. But you have this combination right away. You're saying if I have velocity going in one direction and acceleration going in the other direction, this is true but in the linear world as well. This basically means slowing down. Slowing down is what happens when you have those, when you have velocity and acceleration in opposition. Slowing down. So it's going to slow down and it's going to come to a stop, which is why for part A, they're saying, A, through what maximum angle theta max will the reference line turn in the positive direction? So this is a job for kinematics. Number one, part A, let's do theta initial, theta final, omega initial, omega final, alpha, and T. And I know, this is constant acceleration kinematics. This is part of the kinematics analysis method. This is constant acceleration kinematics, which is one of the very first questions you have to ask yourself. In fact, I think it might be the first question you ask yourself. And why am I saying it's constant acceleration kinematics? That's why. There's no variables there. Unlike the first two problems, there's no variables in this expression. So constant acceleration, which means big five to the rescue. Okay. So let's just play the big five game or the 6-column data table game. Let's see. At time equals 0. So basically this is saying at time equals 0, you're sitting here at 0. That's what this is saying. There's no initial position or there's no starting point. So this rotation does not get a head start and does not get a delayed start. It's just saying, hey, when you start the stopwatch, it's sitting here at 0 degrees radians because my reference line is specified at 0 radians. Look, I embarrassed myself. 0 radians equals 0 radians. Okay, so theta final. This is $sign. Through what maximum angle? So again, it's spinning. It's spinning in the counterclockwise direction, but it immediately begins to slow down and it's going to slow to a stop. Omega initial is given as 9.3 radians per second. That is a given. Omega final, well, if it slows to a stop, when it attains its maximum angular displacement, theta max, at that moment, the angular velocity, omega, is just instantly or momentarily equal to 0 radians per second. And this was given to us as negative 0.35 radians per second squared. So this looks very familiar. This is literally exactly what we've done a bunch of times in the world of kinematics. And I guess we can solve. T is, I don't know, I might not care. Maybe I do care at some point. But right now, play the big five game. Which of the big five equations has the $sign? Here's the $sign with all other variables known. So I think there was only one of them that didn't have the variable T in it. All right, and that was this. That was omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. And just to point out, remember we had VXF squared equals VXI squared plus 2A sub X final minus X initial. So you don't have to have these memorized. You just, you know where they live in your green sheets, and you have to know how to apply this stuff. which is where the practice comes in. So step number 3, at what maximum angle theta max? So I guess, so isolate theta final. Isolate theta final and solve. Okay, let's do that. Omega final. 0 squared okay. Radians. Okay. What's the first and second times of reference line will be at theta max over 6. So I'm going to, if you're still finishing up the calculator part, I will silently move forward. Okay. So this is what happens. This flywheel immediately starts to slow down, and then it reverses direction. So basically, it's going to be spinning. Let's see, what's its 123 radians. So 123 radians is a lot of revolutions. If I divide by 2 divided by pi, that's basically 19 revolutions. So this thing is going to spin 19.6 times before it comes to a stop. So if I'm just thinking out loud here, it's going to spin 1, 2, 3, 4, 5. It's spinning, 18, 9. It's spinning about 19 times, and then it just comes to a stop at some point. And then it starts to reverse, and then it starts to go backward the other way, like that. All right, it starts to go clockwise. So I'm slowing down, and as I'm slowing down, I'm going counterclockwise, and then I stop, and then I start to go clockwise, which is why it's saying, I'm going to hit this value twice. I'm going to hit this value once during the counterclockwise motion. So I'm going to once during slowing down, once during the slowdown, and then once during the speeding up. Once during deceleration, once during acceleration. I'll just write it once during speeding up. So I will hit that particular point, angular position, twice, speeding up. All right, so this is what we have to find. So number five, way over here, let's do a new kinematics table. Okay, so I'm going to have theta initial, theta final, omega initial, omega final, alpha, and T. Okay, now I got to be careful. What's the first and second times the reference line will be at that particular point? So, all right, being careful here. Theta initial is still 0 radians. I'm starting right at the starting line. I'm not getting a head start, and I'm not starting from behind. Theta final, first and second. So this is going to be theta max over 6. I'm going to take my answer to A and just say, hey, my theta final is whatever I got to part A, which is theta max divided by 6. I got to make sure I stored that. Store alpha A. Okay. omega initial 9.3 radians per second, 9.3 radians per second. Omega final, first and second time. So I don't know what omega final is. What's the first and second times the reference line will be at theta max over 6. So I don't know. I don't know. I do know this. It's constant acceleration kinemax. So that's negative 0.35 radians per second squared. And T is the dollar sign. That's step 6. I just want to be careful. I am starting. So I'm just going to go back and double check myself. I am starting from scratch, starting at 0, starting at the starting line. When do I get 1/6 in my case to my max value, both on the slowing down phase and again on the speeding up phase? Okay. This is my initial that was given as 9.3. Okay, got that. I don't know, and I might not care what my velocity is, angular velocity is at those moments. This is okay, so I guess that's good. Let's go on and play the big 5 game. I'm going to guess. I'm just going to guess this. I'm going to guess theta final equals theta initial plus omega initial T plus 1/2 alpha T squared. Again, this is the analog. This is the rotational analog to X final equals X initial plus VX initial T plus 1/2 A sub X T squared. So they do seem to have that analogy between them. And then I guess we're going to solve for T squared. So there might be a little bit of processing here. It's not quite yet plug and play. Number 8. Let's just see here. Theta final is A over 6. This is going to be secant A over 6. This is going to be 0. This is 9.3. Okay, so I think I have a quadratic. 9.3 radians per second. A quadratic does make sense because there is 2 values. There's the value you get during the slowdown, and then that same value when you stop and then speed up and go in the other direction. And I know this. All right, so all right, here it goes. Here's my quadratic, I suppose. Well, maybe not quite yet, but I have A over 6, calculator memory location A, divided by 6 equals 0 plus 9.3 radians per second times T plus a negative 0.35 plus a negative 0.35 radians per second squared over 2 times T squared. So then I'm just going to do this minus A over 6 equals 0. So I'll bring this A over 6 over to the other side. So in the world of quadratic equations, I'm going to have T, well, I'll have AT squared plus BT plus C. So this would be my A term. This would be my B term, my linear term. And this would be my constant term. So off to a quadratic calculator to do this. You should know how to do it on your calculator, or I guess if you don't quite yet and just need to get the right answer now, you can just go to online quadratic, just Google quadratic calculator and plug your numbers in that way, or use the quadratic equation, which is quite honestly not recommended, even though it sounds like the most courageous approach. But I'm just going to use a quadratic equation solver. Here's my squared term. negative 0.175. My linear term is 9.3. My constant term is negative a over 6. Negative 20.59. Negative 20.59285714. Solve. Okay. Here's I'll paste this. All right, when I do my quadratic equation chore, this is what I get. Right there. Okay. So the first time I hit that magical angular position is at 2.3 seconds. It's 2.3 and some change seconds. That should be this answer here. And then I slow down reverse direction and I hit that same spot again at 50.8 seconds. Okay, so we are officially done with A, B, and C, although if you're still hammering away on the quadratic, but that's where practice comes in. The more you do this, the faster it goes. Okay, then I'm going to just forge ahead, and then we can go into our first break after we just finish 2 more parts here. 8. Let me zoom out. Okay. So now, at what negative time and positive time will the reference line be at theta equals 12 radians? Or is that negative 12? I think it's negative 12. Let me zoom in. Yeah, negative 12 radians. So this is just a job for another 6-column kinematics table. Step 9. I'm going to do it again. Theta initial, theta final, omega initial, omega final, alpha, and T. At what negative time and what positive time will that reference speed line? So, all right, so here I'm starting out at 0 radians. And then it says at what negative time and what positive time will the reference line be at theta equals negative 12 radians? Let's see. Negative 12 radians. 12 radians times 360 divided by 2 pi. Negative 600. So it's basically almost 2 reverse revolutions, almost 2 revolutions. It's basically saying at what negative time and positive time will the reference line be at negative 12 radians, minus 720. All right. So let's see, back to the kinematics table. Theta final is negative 12. And I'm going to hit that point twice. Negative 12 radians. Okay. Omega initial still starting at 9.3 radians per second. Theta final at what time? I don't know anything about theta final. This is still minus 0.35. Yeah, so, and this is sort of the same thing, I guess. Time is my dollar sign. When do I hit that mark? I'm going to hit it twice, once during the slowdown, once again when I stop in reverse direction and speed up. So is this really the same thing? Theta final equals theta initial plus omega initial times time plus 1/2 angular acceleration times t squared becomes theta final is -12 equals theta initial, which is 0, plus 9.3 radians per second times time minus 0.35 over 2 times time squared. So it's just another exercise in the world of quadratic equation solving. So 0 equals 12 plus 9.3 t minus what is 0.35 divided by 2 is 0.175. Okay, so this, unless I'm missing something, this is just another again task of finding out when do I hit this point during the slowdown and again during the speed up. So I'm just going to update my quadratic calculator here. My constant term is 12. My linear term is 9.3. Okay, so already go. All right, so when I enter it into my little quadratic equation solver online, this is what it spit back at me. So negative time. So if you can go back in time, your flywheel is going to be precisely at that particular location. And then at some time greater than 0, it's going to return to it. Okay. So we have just done 3 problems in a little more than an hour. This is unprecedented. So it's 7:07. Let's go to chapter 10, quiz 4. And now all of a sudden we transition from kinematics to force analysis. So these first 3 quizzes we're just straight up kinematics, and hopefully you're buying what I'm trying to sell in that, hey, it's really kind of pretty much the same thing with some notable nuances, but we've kind of covered rotational kinematics via the kinematics analysis method. Now we're going to cover rotational dynamics versus just regular old linear dynamics via the force analysis method. And this is the recipe. So this is the same recipe, but now the recipe's expanded a little bit to deal with stuff moving in a circle, stuff spinning, stuff rotating. All right, so this is an Atwood machine. We've seen this before. There was a homework problem, I think in chapter 5, that was this exact same problem, Atwood's machine. The only difference between now and then is we don't assume this pulley is massless. Okay, so that changed, that makes things more realistic and complicates things. And you could say, well, Chris, if you used a lightweight enough pulley, you could ignore it, couldn't you? And the answer is yeah. But what if you can't use a super lightweight pulley, at least relative to these mass values? All right, so let's do our very first rotational dynamics problem. We know the value of M1. I know that value. I know the value of M2. That's given. There's no friction, so we don't have to deal with non-conservative work stealing energy. I know the radius of the pulley when released from rest. So I do know some kinematics. Block 2, when released from rest, block 2 falls 78 point. In my numbers, I'm just going to go straight to meters. So this falls from here to here. And actually, I'm going to do this. Well, all right. It falls 78 centimeters in 5.4 seconds without the cord slipping. What's the magnitude of the acceleration? Let's do part A first. And if you remember, which you should, because this was literally days ago that you were having to apply this. The force analysis method, among other things, said free body diagram. I think it started with free body diagram. Let's do that. So again, great news. This is just a revisit of stuff that's already come before. Here's the, this is the weight of M1. This is the weight of M2. This is the tension pulling up on mass 1. This is the tension pulling down on the pulley. Like that. This is the tension pulling up on mass 2. This is the tension pulling down on the pulley. And I need to very carefully label everything because things are a little bit different. All right, this is the weight. So this is going to be M2G. This is going to be M1G. So weight is pulling down, that is for sure. I'm going to call this T1. I'm going to call this T1. These two tensions are equal. There's nothing disintermediating them, meaning there's no middle broker. There's nothing in between. There is nothing in between M1 and the pulley, just the rope. So that's why I'm saying these are the same. This rope tension on the left side is the same pulling down on the pulley as it is pulling up on M1. So I am purposely talking about that a lot because these are the finer points. These are common tripping points. On the other hand, this is T2, the tension of that rope pulling down on the pulley, which is going to be the same as the tension of that same rope pulling up on mass 2. And these are also the same. So you're thinking, yes, we've been there. But now here's what's different. This is what's different. T1 is not equal to T2. So this is a big deal. The intermediate mass, because there's an intermediate mass, because there is an intermediate mass. So that's the complication. That's the extension we have to do with the force analysis method, because there is an intermediate mass. Okay, so that is one. This is definitely an asterisk. This is something that's new and different. Just like the other asterisk, I would say would be the whole birth of a radian. All right, so those are my free body diagram done. I am done with my free body diagram, I believe. Okay, so then coordinate systems. Coordinate. So let's just, I'm going to write it like this. I kind of like this term. Set up a flowing coordinate system. All right, so here's how my coordinate system is going to flow. It's going to, I guess one question is, do I know the direction of acceleration? That's the litmus test. Do you know the direction of the acceleration? Yes, I do. M2 is greater than M1, so I do know the direction of the acceleration. Maybe I'll just repurpose this vector. The direction of the acceleration is in this direction. This is the acceleration of M2. I do know that's the direction. So I'm going to flow with it. Here's my flow. Ready? I could just say, well, ready, let's just flow with it like that. Let's try that again. Flow. Okay. So flowing, I'm flowing with all. There's three masses here. So this is a 3-mass problem. This is a 3-body problem. I actually have 3 objects, and all of these objects are flowing in unison. They are flowing together. So that's why I'm going to call this plus y. I'm going to call this plus y. And then here's something new. I'm going to call this plus alpha. Okay. So that's my coordinate systems. not quite done with that, but this is like, hopefully all that makes sense. Hopefully I'm being coherent when I'm specifying this as the positive y direction for M1. I'm specifying this as the positive y direction for M2, and I'm specifying this as the positive direction for alpha, which in this case is, this is breaking the convention. I'm basically saying here, I'm saying, note, alpha is positive plus alpha in clockwise. We've been saying counterclockwise. I've been saying counterclockwise is the convention for positive, but now we're flipping that, and we have to, or it's convenient to. All right. So there's my coordinate system. I don't have to worry about decomposition, but I'm going to write it down. Is there any decomposition? There's no decomposition here. Everything's one-dimensional. It doesn't make sense to decompose this alpha. Decomposition done. My flowing coordinate systems are done. The one other thing I should mention is, and this goes along with the coordinate systems. Maybe I should call this flowing coordinate system and AOR. Flowing coordinate system and axis of rotation. AOR for short, axis of rotation. Here's my axis of rotation. That pulley is spinning about an axis of rotation right there. So I'm going to refer to this as my axis of rotation right there. AOR, axis of rotation. And you'll see why we're definitely going to use that, but it's officially part of the force analysis method going forward, now that we're dealing with stuff that spins. And it's not like this force analysis method is going to keep getting, heavier and deeper and wider. Now, pretty much after we make one more adaptation to encompass rotational dynamics, that's it. Then it's universal at that point. All right. Anyway, and then we would do the inventories. But I guess before I do the inventories, I'll write that down. In terms of the recipe, then I would have either an X force inventory and or a Y force inventory and this is the other wrinkle, a torque inventory, tau subscript I. More on that later. But for part A is just all about kinematics. So part A just wants to say, what is the magnitude of the acceleration of the blocks? So I'm just going to use kinematics because I think I have enough information. I'm going to have Y initial, Y final, Vy initial, Vy final, A sub Y, and T. So just straight generic kinematics. Y initial is 0. So, I'm going to focus on M2, cam for M2. I'm going to focus on mass 2 because they gave me data for mass 2. Block 2 falls 78 centimeters in 5.4 seconds. All right. So in that case, this would be right here. This would be Y initial. This would be Y final. So Y initial, I'm going to call 0. No reason not to. Y final, it falls 78 centimeters, 0.78 meters. Did it start from rest? Yes, it started from rest, 0 meters per second. Vy finals, I don't know, and I probably don't care. This is my $sign. And time, I fell 78 centimeters in 5.4 seconds. So this looks to be a very kind of rudimentary kinematics problem. I'm going to say, what's a good thing? Vy final. No, I don't want to do that. I'm going to try this. Y final equals Y initial plus Vy final T minus 1/2 A sub Y. Yeah, I don't want to do that. Vy initial T plus, I guess I'll try this one. Before I get too far down the road here, Do I know one y final? Yep. Yes, I know y initial, vy initial starting from rest. So this looks pretty easy. I know t. So let's get a numerical answer to part A and then go forward. So A equals 0.05 and some change. Store alpha A. 5349 meters per second squared. Back to that. Back to linear acceleration. This is the answer to part A. All right. Now we have to figure out what's the tension. T2, the tension on block 2, and T1, the tension. Right, so now, time for force analysis method. All right, and I've done some of the lifting already. I did my free body diagram. I flow the coordinate systems, flowing coordinate systems, and I specified an axis of rotation. There's no decomposition. And now it's time for inventories. How many inventories should I do? The answer is enough so that you get enough simultaneous equations. Do I need to do an, well, I can say one thing. I don't need to do an X force inventory because there's nothing moving in the X dimension. So I'm going to be considering a Y force inventory and a torque inventory. Let me start with the Y force inventories. All right, so for M1, the sum of all of those Y forces equals, I've got T1 pulling up minus M1G pulling down. And this is where I have to be really dependent on my free body diagram. That equals M1A. Say something about acceleration. The acceleration for M1 is going to be equal to the acceleration for M2. And then here's something new, is going to equal alpha, or I'm sorry, A over R equals, I'm going to do this. Acceleration of mass one. Mass one is going to accelerate at the exact same rate as mass two. Let's just call it A. And then I can say something else here too. A is going to equal R, the radius of that pulley, times alpha. So you're looking at this and you're thinking, yeah, okay, I got it. I understand how mass one is accelerating at the same rate as mass two. So let's just call it A for simplicity. And then this is what's new right here. So a quick word about what the heck that is. This comes from birth of a radian. So here's birth of a radian. Theta, here's how a radian is born. A radian is born via arc length divided by arc radius. So here again is my little piece of my pizza pie slice. This is R, this is S, this is theta. And that's the definition of what a radian is. So I'm just going to rearrange it. If theta is S over R, then S equals R times theta, R times theta. If I just decide to walk up and divide both sides by time, this is what I have now. I have another birth of a radian expression called V, because S is distance. Distance over time is velocity. R is constant, so that just sort of stays out of the fray. R is constant. Theta over time is omega. So that's so this is big bore. So this is bore number one. This is bore number two, birth of a radian number two. And then at one more time, I'm going to go up and just divide both sides by time. And velocity over time is acceleration. So this is acceleration. R is constant, so it just stays out of the fray. And omega over t is angular acceleration. So this is bore number three. So that's these are three very helpful equations that connect the linear world to the angular world. This connects linear acceleration to, this connects linear position to angular position, linear velocity, it gets connected to angular velocity, and linear acceleration gets connected to angular acceleration. So now you know where this comes from. This comes from right here. Okay, so that's a big chunk of conversation just about acceleration. So that's it, I guess. So where's my dollar sign? Well, here's my dollar sign. My dollar sign is right here. There's T1. This is my dollar sign. I can solve for this. So am I missing something? I know M1. I know G. I just figured out A. All right, so let's solve for T1, number 7. T1 equals M1 times A plus G. And I have my acceleration living in my calculator, plus 9.8. Convert from grams to kilograms, 0.43, 4.23 and some change. That's interesting. That's interesting. Let's see. All right. There's A plus 9.8 times M1 is 0.43. All right. 4.237. Newtons. I'm going to put that in calculator memory location B. Store alpha B. Alpha A contains my acceleration. Okay. That's T1. That's T1. I just saw for T1. All right. So going out of order, apparently. But this was the answer to part C. Part C wanted T1. Part B wanted T2. So I guess my first reaction is, well, let's do another inventory. Let's do an inventory for mass 2. Number 8 for M2. Sum of all those y-dimension forces acting on mass 2 is T2, which is negative T2, I should say. Negative T2 is going in the negative y direction. Negative T2 plus M2G, that's Newton's second law, equals mass times acceleration. Got it. Say something about acceleration. Repeat number 5. No, repeat number 6. Okay, so I have my statement about acceleration. Then I'm going to basically say, well, T2 equals M2 times G minus A. Okay. Oh, here's the difference. They wanted you to use 9.81 meters per second. So I'm going to just update. I'm going to update this. All right, so I'm just going to erase this. I was wondering why I was getting a slightly different answer, and that's why. Okay, so alpha A plus 9.81 times 0.43. Store alpha B, okay. Calculator memory location B. This was the answer to, technically speaking, part C. And then, all right, so good to go for T1, the tension 1, 9.81 minus alpha A times 0.57, 5.56 and some change. This is the answer to part B. Okay, store alpha C. Let's put that in memory location C. Okay, so that's pretty cut and dry. I mean, great problem, like just basic kinematics, basic force analysis method up to this point. And then here's some new ground we're breaking into. What's the magnitude of the pulley's angular acceleration? So step 11. Once again, birth of a radian has shown that A equals regular acceleration is arc radius times angular acceleration, which means angular acceleration can be expressed as regular old linear acceleration divided by r. And I have that. That's sitting there in my calculator memory location A. That was the answer to part A. And r is the pulley radius. That's the thing that's moving in a circle. That's the thing that's sweeping through an arc. And that radius is 5.1 centimeters, 0.051 meters. So alpha A divided by 0.051. Okay. Radians per second squared. That is the answer to part D, which means there's only one more part. Okay. Part E, what is the rotational inertia? It says caution, try to avoid rounding off answers along the way to the solution. Okay, which is something I'm always trying to preach just for this reason. That's probably why I kind of ignore sig figs, because Wiley Plus doesn't really abide by the rules of sig figs. Number 12. Okay. What's the rotational inertia? So ready. There's something called rotational inertia. Rotational inertia. And again, I'm going to give you the 25-cent recap. The $100 overview of inertia is found in the YouTube video, but here comes the 25-cent recap. Rotational inertia is designated with the letter I, and descriptively, you could say it's an object's resistance to a change in its angular acceleration. Actually, to a change in its angular velocity. Which mirrors the definition of mass or regular inertia. This was a day one thing. This is going back into the pages of time. Mass is a measure. Mass is a measure of inertia. And what is inertia? It's stubbornness. So imagine if you have a massive locomotive, like a 2,000-ton locomotive sitting on the train tracks. If it's not moving, a measure of stubbornness. If you have this massive locomotive engine sitting on a train track, good luck getting it to move because it has a very high stubbornness value. Similarly, if that locomotive is just chugging along at 10 meters per second, good luck trying to speed it up or slow it down. If it's moving at 10 meters per second, it wants to move. It wants to keep moving at 10 meters per second. If you want to alter that, you have to exert a tremendous force because that's tremendously massive, a measure of stubbornness. I guess that's how you spell stubbornness. So there you go. There's the 25-cent version of the $100 rotational inertia overview. Okay, let me just here, just because I can't resist. I'm always interested if I can find any new visuals here. What if I did large flywheel? Here's look at that. This is pretty good. Look at this. That looks massive. This is the world's largest superconducting flywheel power storage system. Well, that is just perfect. Not the best. Well, big enough. I mean, it's not, well, it's pretty big. I mean, look how big. Look how big this flywheel is. And look how massive it is. It's just a very thick cylinder. And then the other thing you notice, most of its mass is around its circumference. So that's because of optimization. The more mass you have around the circumference, the higher the inertia is for a given mass value. If you have just a finite amount of mass, put it all on the circumference as much as you can, and then that's how you get the greatest inertia. And great inertia means, oh, look, here's an engine. Here's a replacement flywheel for your engine. If this is a good picture, yeah, pretty good. So this is not nearly as massive. But then ask yourself, what are these things doing here? Because a flywheel basically evens out your engine's running. If you didn't have a flywheel, and I'll exaggerate, but as your pistons are firing, you go ka-chunk, 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 ka-chunk. And a flywheel basically means it instead of sounding like ka-chunk, 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 it just sounds like, I'm greatly exaggerating. But the inertia of a flywheel basically pulls one piston stroke into the next, one crankshaft angle into the next. So anyway, I just wanted to go off onto that wild tangent. Because now we are about to find the rotational inertia. So step 13. So everything was kind of garden variety until step E. Step E is brand spanking new. So this problem is very helpful, especially by the time we get to step E, because I'm gonna do this. I'm gonna say, I remember F equals ma. That's Newton's second law. Here's Newton's second law as well. Instead of F, I'm going to write tau. This is Greek letter tau equals I alpha. Okay, so let me make a super big deal about this since this is a major component. But here are the analogs. Force is to torque as mass is to rotational inertia, as regular old linear acceleration is to angular acceleration. And everything has a name here. This is torque, and that is Greek letter tau, T-A-U, tau. This is I for rotational inertia. Sometimes rotational mass, I think those terms are used interchangeably. Rotational inertia, and this is still the angular acceleration, alpha, angular acceleration alpha. Okay, so, and this is the side-by-side comparison. This applies in the linear world, linear translational. This applies in the angular world. All right, and that's what we're going to tap into now, because we have a pulley that's living in the angular world. Those masses are living in the linear world. What is the rotational inertia? So step 14, since torque equals I alpha, that means the following. Inertia is simply going to be torque over alpha. And here's great news. I know alpha. Alpha is known. And then number 14, I don't know torque. So number 15, what's torque? Tau. Tau stands for torque. Okay. So 16. T, once again, for the umpteenth time, stands for torque, is force times lever arm. Force times lever arm. Sometimes lever arm is referred to as torque arm, and sometimes they're referred to as moment arm. And to be honest, I actually might use all of those terms interchangeably at some point. So just know that they all mean the same thing. Let me just repeat. Lever arm is the same as torque arm, is the same as moment arm. If I had to guess, I'm thinking this is probably the most mainstream. So maybe I'll probably use either torque arm or moment arm. Moment arm is also applicable when we study angular acceleration. But this is torque. This is torque. Torque, when you want to unscrew the lid on a peanut butter jar and you have to use a lot of that turning force, that's torque. You have to apply a lot of torque to open up the lid to your peanut butter jar. That's torque. A simple example. All right, so here we go. We got to figure out the torque. So it's time for a torque inventory. Just like we have X force inventories and Y force inventories, now we have torque inventories, abbreviated tau, Greek letter tau for torque, torque inventory. So let's do sum of all torques. Sum of all torques about the AOR. I'm going to do a little sidebar diagram here. Here's my pulley. My pulley is sitting right here. Let me try that again. Uh-oh. A better view of it. Here's my pulley. Here's the radius of my pulley. I'll indicate it from the AOR. Okay. And here's my AOR right here. Wait a minute. I think I'm having tech issues. I am having tech issues. Let me restart again. Okay, maybe I go. All right. This is my AOR right there. Let's label that AOR. Axis of rotation, the point about which this pulley is spinning. This is R for the pulley radius. Here's T1. T1 is pulling down over here. Here's T2. T2 is pulling down over here. I better label these things. This is T1. This is T2. And because of the geometry that we have here, I can see that, yes, this is a 90-degree angle. This is a 90-degree angle. I'm going to drop another radius right here. And yes, that tension is at a perfect right angle to that torque arm. And this is a good opportunity to use that term. This is the radius, and then these are both torque arms. This is my torque arm. This is my torque arm, or moment arm, or lever arm. This is my torque arm. Okay, so I've already...
The torque arm is radius, just being absolutely sure I get it.
In this case, it is. In this case,
Okay.
it's just... Well, in general, you could say the torque arm is always going to be the radius of rotation. And it's just very obvious that that's the case here. But that's probably a true statement. But yeah, in this case, the torque arm is the same as the radius. This is my leverage. Like how much leverage does this force have? The answer is right here. So can you imagine if the radius was much bigger, you'd have a lot more leverage. So the bigger the radius, what's that?
So would the torque of a door be the radius of the hinges, or the radius of the door, or the length of the door?
If this is your door, so here's your door. Here's your doorway with the door, and then it's hinged here. So you have a hinge here, and then another hinge here. And then you walk up to this door and you want to swing this door open. So I'll try to draw it in 3 dimensions, but I'm going to apply a force like this, maybe pulling it out. Maybe I'm pulling the door out that way. So this would be the force I'm applying to that door. This would be the torque arm right here from there to there. So in this case, this is the torque arm. This would be the radius of rotation as well. All right, so that's the example of a door. Okay, so again, I went on record as saying whatever is happening in this direction is going to be positive. So this is positive alpha. All right, so now here comes the torque inventory. I started here, but let me clear the decks a little bit. Sum of all, so this is just F equals MA in the rotational world. Number 19, sum of all those torques. Well, I might have a torque. I'm just going to break it up. I might have a torque. I have a torque due to tension 1, and then I have another torque due to tension 2. Both of these tension forces are producing a torque, and whatever those torques are, they blend together to equal mass times acceleration. But in the angular world, I don't say mass, I say rotational inertia or rotational mass. And I don't say acceleration, I say angular acceleration. Okay, so let's keep going. This is number 20. Torque is torque times force. I'm so ready. I have this. I have T1. There's my force. Here's my lever arm. T1 times R. Now, here's the other thing. This is producing a negative torque. Look at what T1 is doing. T1 right here is trying to spin my pulley in this direction. This is the direction that T1 wants to spin the pulley in that direction, which is in the negative direction. Again, we are on record as saying this is the positive direction for acceleration as far as the pulley, angular acceleration. Why do we do that? Why did we flip our convention? Because we had to go with the flow. So T1 is trying to produce a negative spin, and T2 is trying to produce a positive spin plus the force times the torque arm. That's it. T2, just to belabor the point, look at, here's T2. So if this is you pulling down on T2, cranking on this T2 string, you are basically trying to get this pulley to move in this direction, which is the same as the direction right here that we specified for positive angular acceleration. So that's why this is a plus, this is a minus. What I'm covering here, this is a very common tripping point. Make sure you are really clear on keeping track of all these directions. The devil is definitely in the details. Just make sure you're super clear on that. And then life will be good. All right, equals I alpha. Okay. So let's finish this by saying I does equal torque. Here's torque. Torque is going to be, I'm going to factor out a common term. So here's torque, R times T2 minus T1. So my numerator right there is torque. I'm just processing step 20, all over alpha. Okay, so what is R times T2 is sitting there in memory location C. I'm going to take memory location C minus T1, and T1 is in memory location B. All of that divided by alpha, and alpha is sitting here somewhere. Alpha is right here. Did I put that in? Yeah, store alpha D. All over calculator memory D. Okay. So R is 0.051 times alpha C minus alpha B divided by alpha D. 0.06 and some change. That is, but check out the units. 0.06417. If I did, I'm going to do a quick dimensional analysis. Units for R, meters. Units for torque, newtons. Units for alpha, radians per second squared. So from a dimensional analysis, what the heck is a Newton meter all over radian per second squared? Now here's the secret. Remember, technically speaking, radian is not a unit. So I'm just using this as a placeholder, but radian is not a unit. So then the question becomes, what is a Newton meter times second squared? And then I guess I'm going this way. Kilogram meter per, a Newton is a kilogram meter per second squared times a meter times a second squared. So ta-da, there's a reason I'm spending a large amount of time doing the dimensional analysis. I do end up with kilograms times meters squared. In the good old days when we were dealing with inertia, it was just kilograms, but it's not just kilograms anymore. It's kilograms times meters squared. And it's good to know that. It spent a lot of time on dimensional analysis. We are completely done. So this problem, I think, is a really good problem. This is a really good problem to look at as our first dynamics problem, angular dynamics, because it's pretty heavy. It's pretty heavy and it's pretty complete. Okay. What time is it? That's a lot of time.
Excuse me.
Yep.
For some reason, my like the initial or inertia rotational isn't coming out correct.
The initial acceleration? You mean the
the rotational inertia. That's it.
Part what? Part E?
Part E, yeah.
You got A through D, correct?
Yep. Mm-hmm.
So let's just
I'm like plugging it in right.
So you said I equals what was your radius?
My radius was 5.4, but really 0.054.
0.54. What was your T2?
My T2 was 5.85225135.
5.85. What was your T1?
It was 4.73.
All over. What was your alpha?
It was 1.0416.
All right, so according to your Wiley Plus,
Mhm.
this was given to you 5.4 centimeters.
Mhm.
This was the answer to part A,
B.
T2.
Mhm.
B is right.
Mhm.
You're right. And then this was your answer to part C. Yeah.
Yeah.
And this was your answer to part D.
Yeah.
Okay. I mean, how complicated can that be? 0.054. Did you use 9.81 for G?
Yeah.
Okay. 5.
I got 'em all right.
5.85 minus 4.73 divided by 1.0416, 0.058 and some change.
Yeah. It just won't. It keeps like making a red box.
The red box of shame.
Yeah.
All right, let me take a look. This is chapter 10. Chapter 10 was 4. It's thinking your answer is all right. All right, it believes your answer is 0.057879, which is within that 2%. So, I mean, you're definitely getting an answer within 2%, but here, let me just show you what I'm looking at right there. It's thinking this is your answer.
All right.
So here,
I got it.
okay.
But
So just a
I don't
bug,
know.
a bug. I mean, you're
Okay.
doing it, the real thing. I mean, yeah, you care about the points, but you care about doing things the right way, and you are. So,
Yeah.
okay.
Thank
so,
you.
Yep, you're welcome. Let's do this. Is 8:08. Let us continue to make progress at a nice rate. Slowing down. I'm intentionally slowing down when we talk about stuff that I know historically are tripping points. Okay, so it's another flywheel. And again, here's another, just for show and tell. Here's an industrial strength flywheel. Again, notice how intentionally the mass is concentrated along the circumference of the wheel. That's because the more you can have the mass for a given mass, if you have a given amount of mass, the more you can locate that mass further away from the axis of rotation, the more inertia you get. And there are a lot of situations where you really do want huge inertias. You want this device to be very stubborn in terms of having its angular acceleration change, angular velocity change, I should say. All right, so here's another flywheel. And there are 3 forces acting on this flywheel. I'm going to draw this flywheel face on just to get maybe a clearer view. So I'm just going to take that exact same flywheel and draw it like this, looking straight ahead at it. Okay, so if this is my flywheel, this is my AOR. I have to, that's never an option anymore. This is my axis of rotation right there. I'm going to label it axis of rotation, AOR. That is the axis about which this flywheel spins. Axis of rotation, and I have 4 forces acting on it. Okay, I have F1. So here's what F1 is doing. This is F1. All right, like that. I'm going to label this. This is vector F1, force vector F1. It is a vector, which means you have to worry about magnitude and direction. Here's force vector F4, like this. F4. F3 is going over here somewhere. F3. I don't know if F3, well, okay, F3. Let's say it's going straight down. Doesn't really matter. All right. So this is F3. And last but not least, F2 is also tangential. It's another tangential force like this. I'll try to draw that as a tangent. F2. There you are. Those are all the forces. Here comes the torque arms. All right. And here's a good thing to write down. Torque arm. Torque arm is equals the position vector. Position vector from force to AOR. It's going to get a little more sophisticated than that, but right now, let's just draw the torque arms. Ready? Here's the torque arm for F1. Ready, set, go. That's the torque arm for F1. Here's the torque arm for F4. In fact, F4 does not have a torque arm. Here's the torque arm for F3. F3. Here's the torque arm for F2. I'm going to redo this just to be consistent. So, here's a redo of the torque arm for F1. It's right there. Okay. And I want to indicate the perpendicularity, the orthogonality. These are perpendicular because F1 is acting tangentially. This is perpendicular and this is perpendicular. And again, no torque. That force is not equal to 0, but the torque it produces is equal to 0. There's no torque because there's no torque arm. There's no position vector that goes between the AOR and the force. And I'm going to do this. Torque arm is the position vector from the force line of action, LOA, LOA. LOA, LOA stands for line of action. You'll hear this term a ton of times, just like you hear the term AOR. LOA means line of action. And it's basically the line that contains the vector. This equals the line containing vector. So in the case of F4, here's the line containing the vector. Ready? I'll draw it down here and then I'll relocate it. Let me draw it just down here. Wait for it. This is the line. Wait for it again. Sorry. Okay. Okay, good. Let me relocate it. So this black line, this is the line containing the vector. and it's a line, so it goes off to infinity in all directions. This is the LOA. LOA, line of action. It's the line containing the F4 vector, and there is, there's no offset. There's no offset. No offset means no torque arm. There's no offset. You have no leverage. No offset means no torque arm between the LOA and the AOR. So again, there's no leverage. F4 right here, F4 has no leverage. It's like, this would be like walking up to a door and pushing the door directly towards the hinge, which means you're applying a force, you're pushing the door towards the hinge, but you're not rotating. The door does not rotate at all because there's no component of your force that's at all tangent to that swing path. So there's no torque, because there's no offset. No offset means no torque arm. On the other hand, look at all of this offset. Look at this great torque arm for F1. That's a lot of leverage there. F2 has the same amount of leverage. It's the radius of this flywheel. F3 has a smaller torque. It has less leverage. So this is less leverage, meaning less torque arm, meaning that offset distance. The offsets, and I'm going to draw the LOA for L3. Here's the LOA for vector L3, just to drive home this point. Right there. And I'm just going to put, this is the LOA for F3. So again, I'm stressing this point a lot. This is the LOA for F3. And look at all this leverage I have. That's the offset between the AOR, and the AOR is a vector coming out of the screen. So this is coming in like the plus K hat direction. Anyway, that's a lot said. I am talking a lot about torque arms by design. Okay, so let's see. We're doing the force analysis method. We have to do the free body diagram, which is done. Free body diagram, F1, F2, F3, F4. We have to do coordinate systems. We have to do flowing coordinate systems. And I guess taking clock, it says here, they actually kind of give you a constraint. Taking clockwise direction to be negative, which means counterclockwise is positive. So there's no reason to debate that. Why not? So they're saying take counterclockwise as positive. All right, because clockwise is negative. So here's counterclockwise. Ready, set, go. This is positive alpha. All right, so that makes me done with the coordinate systems. There's no other kind. I don't have to worry about an X and Y coordinate system because there's nothing moving in a straight line. The whole flowing coordinate systems is taken care of. There's no decomposition. So what does that leave? Inventories. There's no X force inventory. There's no Y force inventory. There's only a torque inventory. So here we go. The sum of all torques equals, I have the torque due to F1, and then I have another torque resulting from F2, and then a third torque resulting from F3, and then a fourth torque resulting from F4. And whatever these torques add up to be, it's mass times acceleration, except instead of saying M for mass, it's I for rotational mass. And instead of saying A for acceleration, it's alpha for angular acceleration. So now I have to worry about pluses and minuses. F1, look at what F1 is trying to do. This is what F1 is trying to do. F1 is trying to crank this flywheel that way. Look at what F1 is trying to rotate this counterclockwise. So that's what we're calling positive. F2 is right here. Look what F2 is trying to do this. F2 gets a negative. F3 is trying to do this as well. F3 gets a negative. F4 is equal to 0. So I'm just going to do plus, and then there you are. Okay. This is new. This is the sticky part. So let me be very clear. What is the sum of all my torques? I have the torque due to F1, which is force times lever arm. So it's going to be F1 times F1's lever arm. This is the lever arm. It's the radius of that flywheel. There you go. And then negative minus the torque due to F2, because F2, once again, right here, is trying to spin this disc in the clockwise direction, which we said is negative, and its torque arm is also R, just the radius. F3 is also a negative. This is F2. F3 is also a negative. The force trying to produce this torque is F3. What's the torque arm? It's that little r number. Little r for me is 11 centimeters. I'll just write it as little r for now. And that equals mass times acceleration, but I'm not supposed to say mass times acceleration. I'm supposed to say rotational mass times angular acceleration. Okay, and we'll solve for alpha. So then alpha is going to equal F1, which is 1.8 newtons, times the flywheel radius, which is 0.11 for me, minus F2, and F2 is 6.1 newtons, times the torque arm for F2, which is that same radius, 0.11 meters, minus F3, which is 1.2 newtons, times F3's torque arm, which is 0.04. All of that equals I alpha. What are we trying to find here? We're trying to find the angular acceleration. All right, so there's one more piece of new business coming up here. Things were going so well in step 3. I times alpha. I times alpha. Alpha is the dollar sign. So I'm okay with that being unknown. That is the dollar sign. Now we have to talk about I, the rotational mass. This was a big part of chapter 10. Let me pull up a visual. Here's your textbook. In a second here. All right, and then I actually hand this out. So on exam 3, during exam 3, you're going to receive the following one pager. It's going to look just like this. Okay. There. All right, so here's introductions. This is what you're going to see a lot of times. There are 9 basic shapes that you have to be aware of. There's a hoop about a central axis. There's an annular cylinder. There's a solid cylinder. There's 9. There's 9 of these shapes. Okay, so here's the question. What kind of shape are we dealing with right now? What is a flywheel? This is a flywheel. A flywheel is a solid cylinder rotating about that central axis. So this is what we're dealing with. I'm going to take a picture of this and just bring it right into our notes, because this is the geometry that is in fact the flywheel. Okay, so let's go to the notebook. There it is. Okay. I think a few of these were derived for you in the lecture notes, and you should, again, if you're playing, if your goal is to one day play in this league, the league of a practicing engineer or technologist or scientist, you need to know the derivations. Otherwise, you're heading toward a different league, not a worse league, just different. All right. So anyway, this is it. So I have an expression for the rotational inertia of a disk. It's I equals 1/2 m r squared. Again, there it is, right there. All right, so step number 4, alpha equals 1.8 newtons times 0.11 meters minus 6.1 newtons times minus 6.1 newtons times 0.11 meters minus 1.2 newtons times 0.04 meters. All of that's my numerator divided by my denominator, which is the rotational inertia of a disk, 1/2 mass. What's the mass of my disk? It's 2 kilograms. 1/2 m r squared. What's the radius of my disk? It's 11 centimeters. 1/2 m r squared. 1/2 m r squared. Okay, let's get an answer here. Minus 43 and some change. Time for some dimensional analysis. For sure. My numerator is a Newton times a meter. My denominator is a kilogram meter squared. What the heck is that? Well, I know this becomes a Newton over kilogram meter, and I know a Newton is a kilogram meter squared per second squared. That's my numerator. Here's my denominator, kilogram meter. So when the smoke settles, kilogram cancels with kilogram meter. So you know what I end up with? This is the most interesting part of this problem, the dimensional analysis. I'm ending up with a meter. Oh, this cancels too. I'm ending up with reciprocal seconds squared. This is why this is interesting. So if I do the dimensional analysis, I'm going to get, my numerator is 1, my denominator, because kilograms, kilogram meter per second squared. Let me double check something. A Newton times a meter all over kilogram meter squared is the same as a Newton kilogram meter is the same as a kilogram meter per second squared. Oh, that's a mistake I was making. Kilogram meter per second squared all over kilogram meter. There's a reason, you guys. I'm not going off on some weird obsessive craze tangent. I'm doing this for a reason. Dimensional analysis is really helpful. I do end up, from a dimensions point of view, I am ending up with reciprocal seconds squared. And you know what? That's the same as a radian. 1 over second squared could be written as radian per second squared, because for, I think, the 4th time, a radian is not a unit. Not a unit. So you can technically throw it in anywhere, not a unit. Throw it in. Why do I decide to throw it in here? Because of the context. I'm dealing with a calculation that's spitting out angular acceleration. So I would expect this. I would expect this, and I know, well, to add that radian. All right, so again, lots of quality time on DA. And we get the right answer too. All right, let's see. What time is it? It is now. I say we do one more problem. One more problem, because that's 5 quizzes already. All right, so let me leisurely get our next quiz cooked up. Quiz 6 will be problem 56. Problem 56 is quiz 6. Okay. All right, I think you should now see our last quiz for tonight, chapter 10, quiz 6. Okay. Definitely involving torque. Chapter 10, quiz 6. And I guess we're good to go. So here we have, like, it looks like a teeter-totter, a seesaw, a bar balancing on a fulcrum. If the bar is massless, rigid massless bar, so it's like an imaginary construct. The rod is held horizontally on the fulcrum and then released. What's the magnitude of the initial accelerations of particle 1 and particle 2? All right, so force analysis method to the rescue. Here's my bar. Just draw a thick line for my bar. This is my bar. Here's my fulcrum, my pivot point. Okay, and then I have a particle, particles, each of mass m. So I have a particle on the left side and a particle on the right side. And they each have the same mass m. M for you, m for you. And I got to do my free body diagram. All right, so here's my free body diagram. I have weight pulling down on this mass. I have weight pulling down on this mass. Wait a minute. I have a normal force applied to the massless bar from the fulcrum. Normal force right here. Okay. So this is I'm just going to label even though they're the same mass. That's M1, this is M2. So this is M1G, this is M2G. All right, so how's my checklist doing? My free body diagram, I think, is done. Here's my coordinate system. Here's my flowing coordinate system. Actually, I'll call it. It's flowing coordinate system. And I think it's not moving. There's nothing here that's moving in a straight line. So I don't have to worry about X. I don't have to worry about Y. I just have to worry about the angular, my AOR. And are they specifying the rod is held horizontally and then released? So I'm just going to stick with counterclockwise as positive. So right here, I'm just going to say this is positive alpha because this is my AOR right there. Let me make that larger. This is my AOR right here. That's not a good color. That's conflicting. Good enough. Okay, this is my AOR. So again, I don't have to consider X or Y because everything's moving in a circle. Everything's rotating. Okay, so done with this, decompose, not an issue. And then inventories. And somewhere along the way, I should see what are the magnitudes of the initial accelerations of particle 1 and particle 2. All right. So here goes. Number 1, sum of all the torques. And I have a torque. I'll just write it like this. A torque is produced by M1G. And then I have another torque that's produced by M2G. And then you could argue I have a third torque produced by Fn. And whatever those torques add up, it's going to equal mass times acceleration. And instead of saying mass times acceleration, I'm saying I for rotational mass and alpha for angular acceleration. So now I have to worry about pluses and minuses. Let's see. M1G is trying to do that. So M1G gets counted as a positive. M2G is trying to do that. So M2G gets counted as a negative. Fn is 0. There's no torque arm. I'm going to write it out the long way. There's no offset between Fn's line of action, LOA, and AOR. And just for completeness, this is the line of action I'm referring to for the normal force. Let me position that a little more carefully. That's probably okay. And I can tell I'm going to crash. So let me crash. Yep, and restart. Time out for a restart. Okay. There's no offset between the normal force's line of action, and here's the line of action, this green line. This green line is the LOA. It's the line containing the force vector. So there's no leverage. Fn has no leverage. It has no oomph, no torque arm, no lever arm, no offset. So that's why there's no torque. So step number 2 is, all right, torque is force times torque arm. All right, so for M1, it's positive M1G. That's the force. Here's the torque arm. This is the torque arm right here. And they're giving me, they're saying that's L1. So there's the torque arm for that left side weight force, M1G, minus the torque produced by M2G. Here's the force that's producing the torque. And here's the torque arm. It's equal to L2. What does that equal? I times alpha. And alpha is the dollar sign. Well, no, it's not quite. But the dollar sign lives in the alpha. All right, let's keep going. Number 3. Uh-oh. What's the rotational inertia? What's I? And you might say, well, I'm tempted to say, well, don't worry about it. Let's just look it up right here. There it is. Here's my table of inertias. And all we have to do is find out where the rotational inertia for a point is on this table. And we will quickly find out it's not there. So I have 9 basic geometries that we can work with, but a point is not one of them. And do you know why? That's because the point is the basis for everything. So a little sidebar. Point. The point mass. The point mass, meaning the mass the size of a point, is the basis for rotational inertia. Rotational inertia, also referred to as rotational mass, and depicted with the variable I. All right. So, and that's it. The rotational inertia of a point is defined as mr squared. Okay. So technically you have 10 building blocks, and really the ultimate building block is a point, because every one of these geometries, every one of these inertias started off with a point and then just built up point, just basically glued together enough points in the right geometry to get either a disc or a plate or a hoop or a sphere. So that's why I'm saying the point mass is the basis for rotational inertia. This is the definition. So we actually have an expression. So let's go on to number 4. Ready, set, go. All right, I have M1G times L1 minus M2G times L2 equals the rotational inertia. Here goes. Here's the rotational inertia for M1. It's going to be mr squared. So here's mr squared. Here's the rotational inertia for M2. It's going to be mr squared again, mr squared, L2. This was L2. Okay, times alpha. Let me indicate this. This is L2, and I want to be really repetitive here. This is the rotational inertia for M1, and here's the rotational inertia for M2, and I'm just adding them together because there's only 2 of them. There's only 2 of them, and they're technically they're part of the same object. Well, I guess you could consider them. You know what I better do? I hate to kind of do this, but that's cutting a little bit too many corners. I'm going to erase all of this. Well, not all of it. I'm going to erase this part. All right. Here's the rotate. Let me do it like this. This is a little more courageous. So here's what I'm going to do with this term, I alpha. All right. So I have I alpha. Here is the rotational inertia of M1. It's M1 L1 squared. I got it. Times alpha. Alpha 1, I'll say like that. All right, plus M2 is over there. M2 L2 squared alpha 2. This is better. This is, again, maybe taking the longer path, which is always the right path. What path should you always take? Almost always the longer path. This is the rotational inertia of M1. This is the rotational inertia of M2. Now, here's a great point to make. How does alpha 1 compare to alpha 2? And the answer is they're the same, because they're part of the same rigid bar. They're both sitting there glued to that same massless rigid bar. Alpha 1 equals alpha 2. And then here's sort of my litmus test. Just for the sake of conversation, could you have an angular acceleration for M1 be, say, for example, 5 radians per second squared? And while this is having an angular acceleration of 5 radians per second squared, could M2 have an angular velocity of 6 radians per second squared? No, it can't, because they're both attached to the same rigid bar and they're constrained to move in unison. So they have to always have the same angular acceleration. They're going to have different linear accelerations, but the same angular acceleration, because it's not like this can rotate through 70 degrees in 1 second and this rotate through 90 degrees in 1 second. They're the same. They're fixed together. So that's all I need to say about that. Well, having said that, I'm just going to fight the good fight. M1G L1 minus M2G L2 equals, I'm just going to do one more rewrite here, because I am sure those accelerations are the same. So it's going to be M1 L1 squared alpha plus M2 L2 squared. And they have the same alpha for all of that conversation. And I'm remembering M1 and M2 are the same. So I'm just going to say M times alpha L1 squared plus L2 squared. Okay. Same here. So here's one more rewrite, just because these masses are equal. I have mg times L1 minus L2 equals m alpha times L1 squared plus L2 squared. And I'm assuming I'm not making any mistakes. Let me know if you see anything. But if I'm not making any mistakes, you can see the m's cancel. Let's get an expression for alpha. Alpha, look how simple this looks. What is L1 minus L2 in my numerator divided by L1 squared plus L2 squared in my denominator, unless I made a mistake. But if I didn't, let's get a value for angular acceleration. That's not our final answer. We have to do birth of a radian to get the final answer. L1. L1. 0.4.
Wait, don't you keep G or no?
No, you're right. You're right. M1G. Yeah, it's a very good catch. You saved the day. Good one. Okay. So let's see. L1 is 0.4 minus L2, 1.6 times 9.8 divided by L1 squared, 0.4 squared plus L2 squared. All right, I'm getting negative 4.3 and some change. Negative 4.32 radians per second squared. I'm putting that in memory location A. Okay, let me just do a recalculation. 0.4 minus 1.6 times 9.8 divided by 0.4 plus 1.6. I better redo this. Hang on. Oh yeah, I see my mistake. Okay, same answer. Minus alpha A. All right, number 8 over here. Birth of a radian. Birth of a radian. Once again, said that theta is defined as S over R, which means S equals R theta. And when I divide by time, that's how I get V equals R omega. And then I divide that by time and I get A equals R alpha. So number 9 for M1, let's just look at M1. For M1, I have the acceleration, the linear acceleration of M1 is equal to R1, which is basically the arc radius for M1 times alpha, which I just calculated. All right, so the tangential acceleration for that left side M1 is going to equal its arc radius, which is L1, as shown, times whatever I have sitting there in memory location, calculator memory location A. So I'm going to take alpha A times L1.4, and I get negative 1.72 and some change radians per second squared, but they're saying magnitudes. So as soon as they specify magnitudes, I leave off the negative, and I'm going to just enter, I would enter 1.72 radians per second squared. And then a quick little repeat for M2. So they have the same angular acceleration, but definitely a different linear acceleration. That's a great thing to stress. For M2, the acceleration of M2 is M2's arc radius times that same angular acceleration value. So I'm just going to take alpha A times 1.6 is 6.9 and some change. I get negative, but again, I'm just going to enter the magnitude of negative 6.917 radians per second squared.
Wouldn't the value be meters per second squared?
Oh, you're right. Yeah, good catch. Good catch. And if I had done dimensional analysis, hopefully dimensional analysis would have caught it for me, but you caught it. And you caught it either because you're saying they're asking for A, not alpha, or maybe you're saying, well, I did dimensional analysis, but yeah, either way, you're right. Meters per second squared. Okay. And that concludes today's physics class, chapter 10, quiz 7, our last task for today. It's a meter stick. Okay. So here's the floor. Here's my floor. Okay. Here's my meter stick. Okay, that's my meter stick. That's my floor. A meter stick is held vertically with one end on the floor and is allowed to fall. Find the speed of the other end just before it hits the floor, assuming that the end on the floor does not slip. All right, so this is basically like a hinge. This is kind of hinged in place. There's no slipping going on here. So when it falls over like this, it's just going to fall from here to there. It's going to swing through 90 degrees, fall on the floor, and we need to figure out the speed of the other end. Here's the other end. The other end is referring to this dot right there. That's the other end. We need to find the speed of this dot by when it hits the floor. So there's the meter stick, and here's the meter stick once it has hit the floor. It's just lying flat on the floor like that. And then here's the dot, same dot, but now shown when it's lying flat on the floor. Okay, and this is the velocity we need to find right here. This velocity, the velocity with which it is just running into the floor. All right, so that's our dollar sign right here. What is that velocity? And it says, let's use conservation of energy principle. And it gives you another hint. Consider the stick to be a thin rod. So you know what? Right now, I'm just going to go to the lookup table right here and say, well, here's the one pager that you will have given to you on exam 3, during exam 3. And we actually have this. Which one of these 9 basic shapes is a long, thin rod? Okay, it's right here. Okay, it's right here. Let me make this a little bit bigger. Well, technically speaking, it's not right here, but you know what? This is as close as we're going to get. So I'm going to use this as a starting point. Okay. This is my starting point. So I'm saying, well, it's not exactly this, but it looks kind of similar. So I'm going to paste this here. And I'm saying, well, that's pretty much what I have, except my axis of rotation has been offset. Here's my axis of rotation. My axis of rotation is actually offset down to one end here. So I'm going to move this right there, there. All right, this is what's known. This is the axis of rotation. This is the AOR going through the center of mass. COM, center of mass, right here. Now I've offset my axis of rotation. It's not that axis of rotation. It's actually been offset through this distance right here. And now here's my new, this is my new axis of rotation, also known as my offset, AKA also known as my offset axis rotation. Because again, my axis, here's my axis of rotation. I better specify that. This is my AOR right here, that purple dot. This is my axis of rotation. So again, this axis of rotation is just sitting there at the end of my rod. It's not in the center of my rod. It's been offset from here. It was supposed to be here, and now it's offset here. So that's my offset distance from the center of mass, which is right about here, all the way down to that point. So that's what I'm saying. I have an offset axis of rotation. All right, so this is how we deal with offset axis of rotation. For a rod, I equals 1/12 ml squared. You can see that right here. So do I have a rod? Yes, I have a rod. I have a rod, so it's 1/12 ml squared, but I have to add this offset term plus md squared, where d equals offset value. So this expression that you see right here this expression is called the parallel axis theorem. When I basically have this, I have the rotational inertia about a new axis, a new AOR, is going to be equal to the rotational inertia about the the center of mass AOR, plus MD squared. This is known as the parallel axis theorem, or PAT for short. Parallel axis theorem, the derivation is in your green sheets. A lot of conversation is in your green sheets, although I'm having a lot of conversation here. So this offset, or the new AOR, the rotational inertia around that new AOR, the offset AOR, is just this. So I'm going to get the rotational inertia for this ruler. It's a meter stick. It's going to be 1/12 ml squared. I'm kind of just writing down the same thing. So here, it's going to be 1/12 times the mass. Do I know the mass? No, I don't know the mass. At some point, it's going to probably cancel out. Do I know L squared? I do. L is the distance. What is the rod length right there? What is the length of this rod? Well, that's easy. It's L is 1 meter because it's a meter stick. How great is that? So this is going to be 1 meter, 1/12 ml squared plus m times d squared is 1 squared. All right. Because, oh, sorry. Not right. D is the offset distance. D is 0.5 meters squared. I'll see what is 0.5. Okay, so let me be careful on that. Right here, 1/12 ml squared. L is referring to the rod length, L. D is referring to the offset between the the center of mass, which is right here. There's the center of mass, and there's my offset, AOR. This distance right here, this is L over 2, or just 0.5. Okay, that's good to know. So this equals 1, what is 1/12 m plus 1/2 m? No, not 1/2, 1/4 m. What is 1/12 m plus 1/4 m? 1/4 is 3/12, so this would be 4/12 m, or m over 3. This is the rotational mass. The rotational mass of my meter stick, because it's not spinning about its axis. This is the AOR. It's not spinning around that point. It's been offset down to here. This is the offset AOR. And I have the same drawing going on over here as well. All right, so that looks okay-ish. Let's do energy analysis. Here's energy state A. Let me erase this. They actually they gave you that suggestion. There's other ways to do it, but energy analysis is typically the most economical. All right, so here's my center of mass. This is where everything is concentrated. Right here at that red dot. This is energy. This is my center of mass at energy state A. Here's that same center of mass at energy state B, right here. Okay, energy state B. My center of mass, which is the point at which all the material can be considered to be concentrated, starts at energy state A and then falls over to energy state B. So if I do energy analysis, 1, 2, 3, whatever energy I have at A plus whatever external non-conservative forces are stealing energy or adding energy equals whatever I have at B. And this quickly becomes kinetic energy at A. But you know what? I actually have 2 flavors of kinetic energy. So this is new. It could be translational kinetic energy at A plus rotational kinetic energy at A plus UGA, there's no springs, WNC is going to equal 0, but I'll drag it along. And then again, I want to stress, I now have two flavors of kinetic energy. Translational, which is stuff moving in a line, plus rotational, which is stuff rotating. And I better put B. This is energy state B. Okay. B plus UGB, gravitational potential energy. And there's no springs. And the only thing I have to add here, I have to add a baseline. This is my baseline. That is a requirement. There is no translational kinetic energy. Nothing's moving in a straight line. No straight line motion means no translational kinetic energy. There's no non-conservative work. There's no gravitational potential energy at B because that's my baseline. So my energy analysis boils down to this. Rotational kinetic energy. Oh, let me do some more low-hanging fruit. This is starting from rest. So there is no rotational kinetic energy. It's starting from rest. Okay, so here's what I have. I have, thanks to energy analysis, UGA, which is the gravitational potential energy of that center of mass point, the point at which all of the rod's mass can be considered to be concentrated, equals rotational kinetic energy at B. Look how simple that became. Number 5, what is the gravitational potential energy of that COM point at A? It's MGHA. I better indicate HA. Here's HA. Well, that's easy. With respect to the baseline, HA is just L over 2 or 0.5 meters. So MGHA is what I start out with. I have all that gravitational potential energy at state A, and I end up with all of this rotational kinetic energy at B. 1/2 I omega B squared. You might remember kinetic energy as kinetic energy equals 1/2 mv squared. That's still true, but that's translational kinetic energy. Here's the analog and the rotational side. It's still 1/2. But here's the rotational version of mass. It's called rotational inertia. And here's the rotational version of velocity. It's called angular velocity. Okay, let's keep going. Because I think this is pretty close to the end. M times G times 0.5 meters, because HA is 0.5 meters, equals 1/2 times I. We did the heavy lifting, is M over 3. M over 3. So this is what you're seeing here. This is I, which is referring to this I, which was figured out over here. Okay. And here's now birth of a radian time for omega B, because they want linear velocity or tangential velocity. Here's birth of a radian. Well, I better do a little sidebar for birth of a radian. All right, so just to remember, if S equals R theta, then V equals R omega. So I'm going to substitute, you know what that means. Omega can be expressed as V over R. And now we have to worry about what is R? What is my rotation axis? It's equal to L. So here, specifically in our case, omega at energy state B is going to equal that tangential velocity at state B. And I could label this. This is actually VB. And this is perpendicular. Tangential velocity is the same as linear velocity. What is the rotation axis? It's L, or L equals 1. So this just equals, because L equals 1, then I'm just going to say omega B equals VB, just because L happens to equal 1. It's kind of hard to write that down because they are different, but I'll let that stand. So VB squared. So I'm going to put VB squared. And now you can see M's cancel, solve for VB. I think so. All right, so 9.8 times 0.5 times 2 times 3 square root. Okay, 5, and that's it. So we now know the velocity with which this point right here hits the floor, thanks to rotational dynamics. 5.422 meters per second. All right, 7 quizzes, unprecedented.